Have you ever wondered how two aircraft weighing nearly 70 tons each can fly in tight formation, connected by a tube thinner than your arm, while fuel flows between them at minus 45 degrees at 900 kilometers per hour, while the turbulence behind the tanker's tail throws everything that enters that zone? A system with tolerances measured in centimeters should either snap apart or seize, and in either case, catch fire. But it doesn't catch fire, and the reason is not where you think. The aerial refueling program has existed since 1923. The first time it was done was over California, two biplanes passing a hose hand to hand between cockpits. The technology was so primitive that pilots simply leaned out of their cockpits and tossed the hose to each other, and still, it worked. Today, the US Air Force alone performs approximately 500,000 refuelings per year. That number means nothing on its own. So picture this: one refueling every 63 seconds, around the clock, 365 days a year, and every single one of them involves the same 5 meters between two aircraft, the same turbulence, the same pilot with hands on the controls. This program changed the logic of war. Without it, a fighter's range is a hard constraint. With it, almost none. A B-52 can reach its target and return without refueling. With refueling, it can fly indefinitely, limited only by crew endurance. This is why, in 1957, 3 B-52s circumnavigated the Earth without landing in 45 hours. 19 of those hours were spent connected to a tanker, and why, in 1991, Operation Desert Storm required more than 46,000 refuelings over 43 days. Without them, the campaign would have been physically impossible. Not strategically, not logistically, but literally, the aircraft simply would not have made it. Most people assume the hardest part of aerial refueling is precision, getting the probe into the basket, not flinching, holding still. But here is the problem: stillness in the air is physically impossible. The atmosphere is not a vacuum. It lives. It presses, shifts, throws. A large heavy tanker cuts through the air and leaves a vortex wake behind it, a turbulent zone into which the fighter flies. The aircraft is buffeted, it responds, and any attempt to freeze only makes things worse, because muscular tension slows reaction time, and a clenched hand on the stick transmits trembling directly into the aircraft. The correct frame here is different. Refueling is not holding still, it is synchronizing motion. Aerial refueling is not two stopped aircraft in the sky, it is two aircraft moving identically. This is the single idea around which everything that follows is built. Now we will go through 4 levels, each of which is evidence. But the central question remains: how do two machines flying at the speed of a bullet synchronize so precisely that 12 tons of liquid can flow between them? A KC-135 flies at 900 kilometers per hour. An FA-18 flies behind it, also at 900. Between them, 5 meters. From the standpoint of physics, they are standing still relative to each other. Relative velocity, 0, or nearly 0. Imagine you are riding in a train and you toss a coin upward. It does not fly backward. It falls back into your hand, because you and the coin are both moving at the same speed in the same direction. An outside observer sees the coin traveling at the speed of the train. You see a coin that simply falls straight down. The same applies to the aircraft. 900 kilometers per hour vanishes the moment both objects are synchronized in the same reference frame. But nearly 0 is not 0. The receiving pilot approaches the tanker slowly, 235 kilometers per hour of closure speed. At this point, he abandons entirely the normal logic of flying, where you look at the horizon, at instruments, at the ground. Here, the only reference is the tanker's tail in front of his nose, and the specialized signal lights on its belly. The ARCS, the Aerial Refueling Control System, uses 4 signal lamps, 2 horizontal and 2 vertical. If the pilot is in the correct zone, the lights show green. If he has drifted forward or backward, they show yellow. Outside the zone, they show red and command an immediate break-off. These lights are the only external reference in a situation where the pilot's own sense of position has already become unreliable, because at 8,000 meters altitude, in level flight, the human vestibular system loses its precision. And there is another effect that rarely gets discussed. Pilots call it tunnel vision. Novices on their first refuelings become so fixated on the basket or the receptacle, on the exact point they need to hit, that they stop monitoring the aircraft's overall position. Their eyes see the target, their body moves toward it, but the aircraft meanwhile drifts imperceptibly off axis, changes altitude, and exits the safe zone. The probe may click into the basket and immediately disconnect because the aircraft is no longer where it needs to be. This is one of the most common causes of emergency breakoffs during refueling. Experienced pilots learn to see both the target and the entire tanker simultaneously, to hold a wide focus in a situation that presses you to narrow it to a minimum. Pilots say that after a refueling, you feel as if you have just completed a full combat sortie, even though you never fired a shot. It is the most exhausting piloting work in aviation, not in terms of physical load, but in terms of cognitive load. But there is another system that no one accounts for, and it breaks apart everything we just settled. Any wing cutting through air generates vortex filaments at its tips. This is not a metaphor. It is a direct consequence of the law of conservation of angular momentum. Air that flows around the wing from below to above at its tip curls into a spiral and trails behind the aircraft. In a heavy transport at cruising altitude, these vortices persist for kilometers behind the aircraft and dissipate slowly. They are invisible, but they are there. The wingtip vortices of a KC-135 rotate at up to 90 meters per second at their cores, stronger than most industrial fans. Flying a wing into such rotation is not just a jolt, it is a sharp roll to which the aircraft responds instantly. Imagine swimming behind a large ship in a storm. It raises waves, and you are thrown against them. But in the case of refueling, you are not just swimming behind the ship, you are tethered to it by a tube, and you must not allow the waves to move you even a centimeter. You are tethered. This is why a precisely defined safe corridor exists behind the tanker, approximately 15 meters vertically and 20 meters horizontally. Outside this corridor, the vortices are powerful enough that refueling is prohibited by protocol, not discouraged, prohibited. A pilot who exits the corridor is required to break off immediately. The FA-18 pilot enters this zone and feels the aircraft is alive. It is thrown downward, sideways, sometimes upward. Every jolt is a deviation from the axis. Every deviation changes the position of the probe relative to the basket. Experienced pilots describe the moment of entering the tanker's wake as recognizable. They know exactly where the aircraft will be pushed, depending on the type of tanker, altitude, speed, fuel load. A KC-135 with full tanks leaves a different wake than a half-empty KC-135. A heavier aircraft produces a stronger vortex. Pilots know this. They prepare. They do not react. This is a learned map of disturbances, a neuromuscular skill that accumulates over years and degrades if not practiced regularly. But there is one more level of complexity. It is not in the air, it is in the design. Two fundamentally different docking systems exist, and the choice between them is not a technical detail. It is a different answer to the same question: who bears responsibility for making the connection? The US Air Force has used the flying boom since the 1950s, a rigid telescoping rod attached to the tail of the KC-135. An operator on board the tanker lies face down in a dedicated compartment and looks directly through a glass panel at the receiver below. He steers the boom using small aerodynamic surfaces built into the boom itself. Rudders and elevators integrated directly into its body. He guides it into a receptacle on the receiver's spine or nose. The receiver holds position and waits. The operator does everything else. The advantage is obvious. Transfer rate can reach up to 2,200 liters per minute. The rigid metal channel maintains stable pressure. A B-52 Strato Fortress with tanks holding over 100,000 liters refuels in roughly an hour. NATO, US naval aviation, and most allied nations use a different system: probe and drogue, a flexible hose with a conical basket at the end. It trails behind the tanker and stabilizes through the aerodynamic drag of the cone, like a small parachute holding its shape in the airflow. The receiving pilot guides the probe himself and drives it into the center of the basket. A click, the valve opens, fuel flows. Think of two countries with different electrical outlets. The voltage is the same, the plugs are incompatible, but the incompatibility here is not only mechanical, there is also a chemical dimension. US Navy carrier aviation flies on JP5, fuel with a higher flash point. This is critical on an aircraft carrier, where a fuel spill in an enclosed hangar can mean catastrophe. The Air Force flies on JP8. Both grades suit most engines, but the tanker must know in advance who it is refueling and with what fuel it departed. This too is resolved on the ground before takeoff. An FA-18C Hornet with its probe-type fitting cannot take fuel from a standard KC-135 without an adapter package. The KC-10 Extender and KC-46 Pegasus carry both systems simultaneously, the boom on centerline and two drogue hoses under the wings. They can refuel 3 aircraft at once, but simultaneous refueling of 3 is a separate airspace management problem. 3 receivers in tight formation behind one tanker, each holding its own zone, without interfering with its neighbor. But there is one more level, and it is not in metal, not in hydraulics. It breaks apart everything we just settled. Automation could have taken over aerial refueling long ago. Technically, the first fully automatic refueling of an unmanned aircraft, Northrop Grumman's X-47B, took place over the Atlantic in 2015. No pilot aboard the receiver, no operator holding the controls. The system performed precisely. The probe entered the basket on the first attempt. The F-35 has an automated refueling assist mode. It reads signals from the tanker, adjusts thrust, and keeps the pilot in the correct corridor. But the final decision remains in human hands. The automation assists. It does not replace. Why? Because automation optimizes for a known situation. A human reads the situation as a whole, including what the sensors have not yet registered. The pilot sees the tanker's tail drift slightly and already knows there is a lateral push coming. He prepares. A sensor would register the push only after it happened, and only then begin compensating. The difference is fractions of a second. At 5 meters from the tail of a 70-ton aircraft, those fractions of a second are the difference between a normal disconnect and a collision. In 1982, during the Falklands Campaign, British Vulcan pilots conducted a refueling at night in the heart of a storm front with one fuel pump failed aboard the receiver. By every parameter, impossible. They refueled. No system provides guarantees. Disconnects happen. Fuel spills into the atmosphere and evaporates instantly at -40. Occasionally a hose strikes the fuselage. In 1966, over Palomares in Spain, a collision between a B-52G and a KC-135A during a nighttime refueling caused one of the most serious nuclear accidents of the peacetime era. 4 thermonuclear bombs fell onto Spanish soil and into the sea. None detonated, but the radioactive contamination took months to remediate. American military personnel removed thousands of tons of contaminated soil from Spain. This is not protocol. It is a human decision made under conditions where no engineering provides a complete answer. Aerial refueling is always a bet that the pilot will manage, not that the system will not fail. Let us return to that pilot in the FA-18 cockpit to the tanker's tail 5 meters away. Now you see something different. Those signal lights on the KC-135's belly, that is the ARCS system, which exists because the human sense of distance in a featureless sky is unreliable, and without an external reference, the pilot loses precision within minutes. The trembling of the aircraft under his hands, that is the vortex wake with filaments rotating at 90 meters per second, a map the pilot spent years learning so that he does not react to the turbulence, but anticipates it. The click of the probe entering the basket, that is probe and drogue, with the correct fuel grade, which places the entire responsibility for the connection on the receiving pilot because someone decided this is the right approach for naval aviation, and the silence in the cockpit after connection. That is not relief. That is the beginning of the 10 most demanding minutes of the sortie. 4 levels, all moving, all in sync. Refueling is not holding still. It is the most precise stance that exists at 8,000 meters altitude, and it happens every 63 seconds.